Hello and welcome to MitoTalk. We talk about power lines and pathways targeting mitochondria with precision medicine. I'm Sukant Khurana, and with me is Basudha Banerjee. Let's talk about this interesting topic. The transport chain is a silent orchestra playing out in every cell. It fuels our lives. But when its instruments falter, energy collapses and diseases takes root. In this episode of MitoTalk, we zoom into mitochondrial membrane, explore its role as a pharmacological frontier, and learn how AI is transforming mitochondrial drug discovery.
So let's discuss about the basics of the electron transport chain, commonly known as the ETC. So deep within the mitochondrial inner membrane lies the electron transport chain, which is a series of protein complexes that moves electron like a current down the wire. Complex 1 through 4 handle this electron relay, and complex 5, ATP synthase, uses the resulting proton gradient to generate ATP, which is the currency of cellular energy. But ETC is very delicate. A single dysfunction in, say, complex 1 can disrupt the entire flow, leading to insufficient ATP, oxidative stress, and diseases ranging from Parkinson's to myocardial myopathies. This is what makes ETC both a source of pathology and an opportunity for intervention. Targeting these complexes selectively is the holy grail for mitochondrial medicine, which makes us understand that mitochondrial membranes are potential drug targets. Unlike the outer membrane, the inner membrane is impermeable and tightly folded, which is a feature very vital for generating membrane potential and ATP. Embedded within it are the ETC complexes, cardiolipin-rich zones, and transporters like ANPs and UCPs. Therapeutics that target this space must cross multiple barriers: the cell membrane, the outer mitochondrial membrane, and finally reach the inner membrane without harming it. Now, drugs like Elamipretide bind to cardiolipin to stabilize the membrane curvature and other functions. Additionally, SKQ1 or MitoQ are engineered to accumulate within the mitochondria using lipophilic cations like TPP. These are designed to harness the very membrane potential they aim to preserve. This class of mitochondria-targeted drugs could rescue bioenergetic failure, reduce reactive oxygen species, and even reverse cell death signals.
Let's talk of AI and mitochondrial drug discovery. I love talking of everything AI. So here's when you are at this stage, AI steps in, not as a scientist, but as a symphony conductor of complexity. Traditional drug design struggles with mitochondria because they are hard to reach and harder to model. But AI trained on protein structures can now predict binding sites on ETC complexes and simulate the effects of drugs on mitochondrial dynamics. We're also using machine learning to analyze patients' omics data, mapping how mitochondrial DNA mutations after ETC performance across tissues. AI-driven platforms can propose custom molecules that bypass damaged complexes or rewire entire pathways altogether. We actually did a lot of work. I'll not get into details this, before a lot of AI, and we did it through simple computational biology. And there's a long story, but the efficiency now can be at least tenfold more in finding molecules than simple computation that we were using. Might even be hundreds or thousands fold more. Imagine generating a list of small molecules that could partially substitute for complex one activity, or design peptides that ferry antioxidants directly into failing neurons. That's happening now in silico. Now let's look at overcoming challenges of mitochondrial diseases. Mitochondrial diseases are notoriously complex. They can come from nuclear or mitochondrial variable onset and affect multiple organs. Using AI-based screening, we can now cluster patient populations based on mitochondrial dysfunction subtype, then match them to personalized interventions. This is precision medicine for the powerhouse, a leap forward from blanket antioxidant therapy. Drug discovery is also going deeper with AI, designing allosteric modulators that fine-tune ETC activity instead of turning it on or off. Think of it like adjusting a dimmer switch on energy output. Future is bright.
We are standing at the edge of a new field that is bioenergetic medicine. It does not just treat diseases, it restores cellular performance. In the future, wearable devices might monitor mitochondrial activity in real time, alerting us to fatigue, illness, or any sort of inflammation before the symptoms arise. Combined with AI, we will be able to dynamically adjust therapy by increasing the ETC support whenever stress is high and promoting repair during rest. Mitochondria may be ancient, but our ability to understand and heal them is brand new. And the mitochondrial membrane, which was once a barrier, is becoming the gateway to longevity, performance, and cellular harmony. With that, we come to the end of this episode, and the ETC chain is more than a power line, it's a lifeline. And thanks to AI and targeted medicine, we are learning to repair, modulate, and even reimagine it. The mitochondria are calling, and the future is listening. Join us next time on MitoTalk. Thank you very much. Thank you, Dr. Khurana.
Thank you.